View of carbonate rocks from Mount Slipper, Yukon that contain apatitic scale microfossils. Fossils are found by dissolving the carbonate rocks in weak acid. Canadian penny for scale. Credit Justin V. Strauss. A critical feature of many multicellular life forms on Earth are hard, biological structures, such as animal bones and snail shells that are made from minerals. Tiny fossils recently discovered in Canada have pushed back the oldest known evidence of biomineralization to 810 million years ago. The finding could yield insights into locating fossils on other planets and shed light on the ways in which life forms and the planets developed together over time. The researchers detailed their findings in the journal Science Advances. They received financial support from the NASA Astrobiology Institute MIT Noden through a NASA Astrobiology postdoctoral fellowship. 5 bold claims of alien life. Multicellular organisms, such as animals, plants and fungi, are all examples of eukaryotes, whose cells possess nuclei. The evolution of biomineralization was a key milestone in the history of eukaryotes and for Earth in general, since biomineral structures, such as coral reefs, have had a dramatic impact on the planet's geology. Yet, early signs of eukaryotic biomineralization have remained obscure in the fossil record, making it difficult to know the age and environmental circumstances in which these biological structures first emerged. View of Mount Slipper looking towards the layers of rock that contain biomineralized fossils. Credit Phoebe A. Cohen to pinpoint when eukaryotic biomineralization might have first evolved. Scientists collected samples from a roughly 200-foot thick 60-meter section of lime mudstone and black and gray shale near Mount Slipper in Yukon Territory, Canada, near the Alaskan border. We were there in late June, but it was still really cold, said lead author of the study, Phoebe Cohen, a paleobiologist at Williams College in Williamstown, Massachusetts. There was lots of snow still on the ground, but that was actually okay, since that's where we get our drinking water from. The researchers focused on microfossils within the rock, which arose during the Neoproterozoic era between 541 million to 1 billion years ago. The mountain slope where the fossils are found is very steep, and much of the rock is loose, so we spent a lot of time precariously perching on steep slopes whacking away at rocks with our rock hammers to collect samples, Cohen said. Scanning electron microscope image of a cluster of biomineralized ASM fossils from Mount Slipper. Fossils are found by dissolving carbonate rocks from Mount Slipper in weak acid. These structures likely acted as armor, with many plates of the same type surrounding a single cell. Credit Phoebe A. Cohen. The microfossils Cohen and her team uncovered, thought to be single-celled marine eukaryotes, come in a wide variety of shapes. Each of the tiny fossils we find we think are its own organism, but part of a single cell. Imagine a round single cell surrounded by these little armor plates, Cohen said. Using high-resolution transmission electron microscopes, Cohen and her colleagues found these microfossils were largely made of complex, interwoven networks of fibrous crystals of a mineral known as apatite. The intricate nature of these networks confirmed they were created by a biological, as opposed to a geological, process, the researchers said. Furthermore, analysis of isotopes of the elements rhenium and osmium in the rock suggested these fossils are roughly 810 million years old, representing the oldest specimens of eukaryotic biomineralization discovered to date. They are, in fact, older than previous specimens by about 200 million years, Cohen said. Eukaryotes were building very complex biomineralized structures much earlier than we thought they were, Cohen said. Early Earth a battered, hellish world with water oases for life. It was a different world during the lifetime of these organisms than today. Almost all of life existed in water, and plants and animals had not yet entered the scene. But there was a large diversity of microscopic eukaryotes at the time. Some of these organisms were algae similar to today's red and green algae, while others do not have a similar modern analog, like the mysterious fossils Cohen's team found. Analysis of the rocks surrounding the fossils suggest that chemical alterations in the oceans when these eukaryotes were alive boosted the amount of phosphate compounds that were dissolved in the water where these life forms dwelled. This, in turn, helps explain why these organisms might have created structures made of apatite, which is a phosphate mineral. And it suggests that biomineralization developed as organisms and their environments evolved together through time, Cohen said. Lots of available phosphorus, then maybe you'll expect to see organisms using that element to biomineralize, Cohen said. This research may also shed light on where to find fossils on other planets. For instance, if looking for fossils made largely of phosphates, scientists may want to focus on areas that were once or are currently rich in dissolved phosphates. We've learned more about the conditions under which these types of biomineralized fossils can be found, which is useful as we begin to explore places like Mars for potential fossil evidence of life, Cohen said. Future research could focus on finding such fossils elsewhere in the world, Cohen said. I'm also working on trying to understand why these fossils are preserved here and how they're preserved, which will help us find them elsewhere and also help us understand more generally how biomineralized fossils get preserved in ancient rocks, she said. There's also a lot of questions about why we don't see eukaryotic biomineralization again for almost 200 million years, Cohen said. Was it because these organisms went extinct? Then why didn't other organisms evolve this capability? Was it because of ocean chemistry conditions? There's many interesting questions to follow up with there as well. This story was provided by Astrobiology magazine, a web-based publication sponsored by the NASA astrobiology program. Follow space.com at space.com, Facebook and Google. Story posted on space.com.